Good morning, everybody. So last lecture, we started chapter 7, which is about entropy and the entropy calculation. And we ended by giving some definitions. Today is beginning of lecture 13. However, we're going to continue a little bit in chapter 12, lecture 12. Then we're going to go back to lecture 13. So we're almost done, guys. This is our 6 weeks. And next week is the last weeks of lectures. And our final is the following one, August, I think 13. So what is going on today? Today, we're going to continue lecture 13. Today is 27th. So we have chapter 7, entropy. Can you see everyone? Can you see that? Can you see that?
Yeah, we can see.
Okay. We give a very simple definition that delta S, like ds, like this, equal delta Q over T. The same way we define, for example, work, delta work was PdV. Something like this, this is the work. If we able to write pressure in terms of volume, P as a function of volume, for example, constant pressure, constant volume, constant temperature for gases, polytropic, we can obtain work by integrating this equation. This equation can be written either in this way or delta Q equal T delta S. Both are correct. Both are correct. For example, if T equal constant, we can integrate. So delta S, for example, ds equal Q over T0 or T constant, this temperature. When this happen? For reservoirs, for example, ambient, ocean, so temperature remain constant. However, this is infinite thermal capacity. A river, whatever you dump hot water, the temperature remain constant. So Q over this, the same for ambient. So this is the first special important case for surrounding. Usually, this is correct if the temperature is constant. Heat over T constant. This is also correct. This is a property. This is not a property, but this is a property, which is delta S or T delta S. Both are correct. Okay, guys? So if you, for example, able to write T in terms of S or S in terms of T, you can get how much heat did you expect. Like this case, you can get Q. So here I can get delta S or heat, both, either correct. The heat addition or rejection, let's say you have a system. If you had heat, this Q is positive for the system, but negative for the surrounding. So you have system, you have surrounding. This Q with respect to system, it's positive because heat addition to the system. But this Q with respect to surrounding is negative. That's why delta S over T equal negative for the surrounding. And if the temperature of the system is also constant, so this term equation like this way, so Q positive, negative for the system. For the surrounding, negative, positive. This is what we took last time. Then we apply that also for steam tables. We learned that there is a new property. We have P, T, specific volume, specific internal energy, specific enthalpy, specific entropy, S small. Again, the same units as internal energy and enthalpy. Joule or kilojoule per kilogram Kelvin. Joule is correct, but the table provided in kilojoule per kilogram Kelvin. This is a very important new property. And we're going to see today how good or important this property is. Of course, we have also X, which is quality only if we have saturated mixture. So this new property is the last 3 columns in the steam table. SF, SFG, and SG. The same way you use U, UF, UFG, H. For example, S equals SF plus X, SFG. If you have quality, if you have mixture. So you can get quality from here or use quality to get S. If it's superheated, it's direct output. You can know it exactly. If it's superheated, just S equal S in the superheated. So this is only for saturated mixture. Saturated mixture. We gave some examples for that. So today we're going to continue. So we stop at the stem table. Today we're going to continue with that by using other things. Okay. And we give a little bit definition for the isentropic. A little bit. We're going to discuss a lot today about isentropic. So in section 7.7, something very important is called T delta S. T delta S relations. There are several relations for T delta S. Remember, delta Q equal T delta S. Oops, ds. So this is D property. This is delta, which is not property. We're gonna get here. So we have kind of 4 cases. Remember this, guys. The first case, we have T delta S. We use it for example, for constant temperature. Just delta S equal Q over T. The second one, we're gonna have it now, or steam table. We can use it for steam table. Using some information, 2 independent intensive properties, countermand. Steam tables, you can get the S, or from S, we can get the rest of the information. So if you have, for example, T and, for example, P, you can get S if it's superheated. If you have rho or nu and S, you can get the rest of the properties. For example, S. We can have liquid and solid that we're gonna discuss right now, or ideal gas. So these two we're gonna discuss now, 7.7, 7.9. So liquid means liquid and remains liquid. For example, water remains water. There is no vapor. So here we have both liquid and vapor. Solid, for example, aluminium, copper, and remains aluminium and copper, but it has some delta S. So how we can get delta S for all of them? So we knew this, but we need to do these two today and continue with lecture, which is lecture 13 as well. So here, the first thing we can discuss is delta Q, as we know from first law. This is the first formula of thermodynamics. For closed system, we have delta Q minus delta W equal delta U. Actually, you can use du. Does anyone did not see this before? Hey guys, does anyone did not see this before? Q minus W equal delta U. So this guys, can you hear me?
Yeah.
So this guy is T delta S. This guy is PDV. If you want to use everything specific, so we need to use U small. So this is per unit mass, this is per unit mass, so this would be specific. This is delta U, delta U. So equation would be T delta S equal this. Or T delta S equal du plus PDV. So everything here is per unit mass, which is specific here. Here, per unit mass, per specific. So everything will be specific. This is the first formula. This is a very important formula. Usually, if we have closed system. How about it? Because you have internal energy. How about it if you set H equal U plus PV? A specific enthalpy, a specific internal energy. Can you see that marker, or is it not good? Maybe you can use another one. So we can use delta H equal delta U plus delta PV. When you differentiate multiplication of 2 variables, you can say it's dH equal du plus 2 things. PDV plus VDP. So fix the first, differentiate the second, PDV. Fix the second, differentiate the first, VDP. But du PDV is d T delta S. So I can remove this by T delta S. So this guy is T delta S. This is equation double star or single star from equation single star. So you can say T delta S equals delta H minus VDP. This is second equation, and that's it. So two equations. Can you see this equation, guys? Can you see this equation, guys? Equation star and double star.
Yeah.
Yep.
So you can say either T delta S equals delta U PDV plus PDV, or T delta S equals delta H minus VDP. Here PDV plus, here minus VDP, but with H. These equations are always valid. Let's talk about the first special case, which is this one. For liquid and solids. Liquid means if I give you cup of water, it was, for example, 30 degrees Celsius, and it became, for example, 60 Celsius. At what atmosphere? This means it remains water. If I give you a stainless steel bar, you heat it up from, let's say, 100 Celsius, or cool it down to 20 Celsius, it still remains solid. This still remain single phase liquid. If it change the phase, nope, use a steam table. For pure liquid and pure solid, the most important thing about liquid and solid, the volume is constant. So if you have this liquid and heat it up or cool it down, the volume does not change. Correct, guys? Have you ever seen somebody heat the water or any liquid, the volume expand? It's incompressible. The same for any solid, copper, aluminium. The volume is constant. So which one has dV? This one has dV or this one? Which one is better? Which one is better, guys? Hello?
Solids.
For both, which one is better? Equation has delta V. This one. So star and double star are valid always. But the star is better because if you put delta V is 0, if you put V equals 0 constant, or delta V equals 0, there is no change in the volume. It means T delta S just du. Here is hard to say. You guys say dH minus, that's not good. So we like to have one variable, that's better. And actually, if you integrate this, you can say delta U here is just C delta T before you integrate C delta T. Why? Because the energy, if you have a system and heat it up, as I told you before, Q, or actually Q small better, is delta U, H equal C dt. So delta Q would be delta U, C delta T. What is C? Heat capacity. Heat capacity. I will extend this later. Delta S can be C dt over T. So delta S is just between T1, T2, S1, S2, just delta S, which is S2 minus S1 equal ln, so C ln T2 over T1. So if you have water, if you have solid, let's say water heat capacity was 4,200, about 200 joule per kilogram Kelvin. So you need this heat to increase 1 kilogram 1 Celsius for water. It's a constant. If you heat from 30 to 60, this T1 and T2. If you want to know how much entropy change, S2 minus S1, it's just C ln T2 over T1. This temperature in Kelvin over this temperature in Kelvin, you can get delta S. And of course, if you want to remember, Q was simply C delta T. This is a heat addition. If you want to know how much heat to go from this to this, heat per unit mass equals C delta T. Do you remember this, guys? So C is heat capacity. For solid and liquids, pure solid and pure liquid, Cp equals Cv equals C. If you remember this, guys, we do not have heat capacity at constant pressure. We do not have heat capacity at constant volume. They are the same, unlike gases. Gases, we have Cp and Cv. That's why it's a little bit harder here. But for solid, we have just one C. So if I ask you in the exam, I want delta S for pure aluminum, pure copper, pure water, with heat addition or heat rejection. So you have initial temperature, final temperature, C then. If this cool down, this delta S will be negative. So T2 over T1 in Kelvin, T2 over T1 ln less than 1, it's negative. Times C, which is constant for this substance, for this material. Do you have any question, guys? Do you have any question, guys? Hello? So again, we want to get delta S. We want to calculate delta S. The whole objective of this class to obtain delta S for constant temperature, like surrounding. Guys, can you hear me? Hello?
Yeah.
Do you have any question for constant temperature system, like reservoir? Delta S is just Q over T. That's it. Q over T. That's it for constant temperature system. For a steam table, if you have, for example, water and vapor, or vapor only. Water, liquid, and vapor. Like you have liquid and vapor, or vapor only, just like superheated, but you still have steam table. The most accurate. There is a special case called for liquid and solid, 7.7. For liquid and solid, we have single heat capacity, just C ln T2 over T1, because volume is constant. So only T delta S equal delta U. And delta U just heat. Heat is CV or C delta T. Okay, guys? Sometimes people write this CV because it's constant volume. Sometimes, but it doesn't matter. Because it's constant. There is nothing called CP for solid or liquid. That's why we say use C. Heat capacity for water, heat capacity for sand, heat capacity for solid, aluminium, copper. Okay, guys? Does this make sense? This is the last part in lecture 12. Let's go now to lecture 13 itself. How about if we have ideal gas? 7.9. How about if we have ideal gas? The same thing. We can use the same equation, star and double star, to prove ideal gas. Before ideal gas, guys, I ask you a question, guys. Ask you a question, guys. If I told you liquid and solid, and it's isentropic. Isentropic means delta S equal to what? Equal to what? Isentropic, adiabatic, and reversible. Delta S equal to what?
To 0.
Exactly, equal to 0. So if delta S equal to 0, what's the condition here, guys? This is only happen if it's isentropic. Similar entropy. What happened? When this happened, guys? So when this is constant, so ln T over T equal to 0. It means T1 equals 2T2, T2, only if it's constant temperature process. So if you have solid or liquid, pure solid, pure liquid, remains solid, remains liquid, the temperature does not change, delta S equal to 0. There is no heat addition. But actually for steam table, you may have temperature the same. For example, if you are working in this saturated mixture, temperature is the same, but you have delta S, huge delta S. Why? Because you have phase change. You're going from pure liquid to pure vapor, or some more vapor. So when you go this way, you have phase change. Liquid became vapor, liquid became more vapor, more vapor, more vapor, until even complete vapor at saturated vapor line. So we have delta S. There is no increase in temperature, but we have delta S. Unlike solid and liquid, if you have the same temperature, delta S is the same. It's impossible to get delta S without changing temperature because there is no phase change. But here we have phase change. That's why the heat consumed to transform the phase from one phase to another. Okay, so here, this case only happened if T1 equal T2, which means temperature does not change for liquid and solid only. For ideal gases, as you remember, ideal gas mean P, V equal RT. This is the ideal gas law, always correct, as long as you have ideal gas. If you have a problem and you heard the word air, O2, N2, argon, helium, nitrogen, oh, actually nitrogen here, carbon dioxide, any gas, you may assume it's ideal gas. Ideal gas, the first thing, ideal gas law, always correct for any ideal gas. It means if you have two independent intensive properties, you can get the third. R from table A1 for this gas. Let's say vapor of air, oxygen, even superheated water, like superheated water. But in this case, I need to say this is ideal gas. I need to say superheated vapor water, I need to say ideal gas. But otherwise, like air, oxygen, nitrogen, carbon dioxide, helium, any gas I said in the exam, you can use ideal gas equations without even thinking. But do not ever, never ever use this equation for water, for solid, for mixture, for superheated water. Do not use it for super, unless I said, how about if we use ideal gas law? How bad it is. Okay, guys? Also, delta U equal C V dt, and delta H equals Cp delta T. These are the equations we used before for ideal gases. Okay, equation star and double star, always correct. Ideal gas, solid, anything, even steam table, it's always correct. But if you can get this information, you can get T delta S, or vice versa. So come and write this here. T delta S equal delta U plus PdV. This is equation star. This is equation double star. I'm gonna remove this here to make space. But these two equations are always correct, no matter what the fluid is. Okay, guys? Can you see, guys?
Yeah.
Okay. So these equations always also correct for ideal flow. For remember, as you remember, if Cv is constant, you can say delta U equal Cv delta T. If Cp constant, you can say delta H integrate equals Cp delta T. It means if you have, for example, P and V, you can get T. let's say state 1, let's say state 1 and state 2. Using a state table, it's easy. If you have P and V, you can easily get T, you can easily get U, you can easily get H, S, anything. From state 1 to state 2, if you have P here, P1 and V1. If you have P2 and V2. Using ideal gas law and R is constant, you can get T1. From T1 and T2, we can get delta U. So it means we can get kind of U1 and kind of U2. You can get H1 and H2. Huh? How about entropy? That's what we're gonna do now. So we learned it from STEM table how to get entropy. Now we're gonna learn how to get entropy for ideal gases. That's even better here, because we have this equation or this equation. Plug in delta U equals CV delta T. So you can say delta U from first equation star. You can say delta U equal to, or T delta U equal T CV delta T plus PDV. The second equation, you can say T delta S, actually this is delta S, I'm sorry, equal CP delta T plus or minus VDB. Correct, guys? From equation double star and equation single star. Correct? What I did, I replaced delta U, which is always correct, or delta H, by the ideal gas correlations, definition of delta U and delta S in for ideal gases. Does it make sense, guys? We wish to get S1 here. We wish to get S2 here, or at least delta S. Like we usually in first law, we need delta S, delta U, delta H, and stuff like that. We don't care about S itself. Okay, guys? Are you following me up to as of here? What I did, I just replaced delta U by this, delta H by this. Does it make sense, guys? Do you have any complaint? Okay, let's divide by T. I want delta S. Let's divide by T. Let's use the first one first. Divide by T, guys. So you can say delta S equal CV delta T over T plus PV over T. Correct? Divide by T became just delta S. Divide by T, CV over T, delta T. Divide by T, P over T, dV. Correct, guys? Correct?
Yeah.
Okay, how about P over T? P over T equal to what, guys? In terms of volume. So this T delta S can be written for ideal gas. This is always correct. Always correct. But this is only for ideal gases, because I replace delta U by this, delta H by this. Only valid if you have ideal gases. So delta S here can be CV dt over T plus P over T equal R over V plus R dV over V. That's great. That's very great. We know why? Because we can see every term. This only has temperature. This only has volume. That's easy to integrate. Integrate from S1 to SC2, from T1 to T2, from V1 to V2. It means from state 1 to state 2, from state 1 to state 2, state 1 to state 2. Here would be just SC2 minus S1, because integration of 1, it's a property. It's S. SC2 minus S1. Yeah. Here, dt over T. Integration is what, guys? CV is constant. Integration of delta T over T is what? Is what? Integration of delta X over X is what? Hello?
ln x.
ln x. Ln x. Ln, logarithmic function of base e, exponential number. E is 2.718281828. Okay? That's called E. Exponential number, it has a logarithmic function, which is inverse function. It's called ln. ln. When you integrate ln, delta x over x, when you integrate delta x, x to the n, this is of course x to the n plus 1 over n plus 1 plus constant if n not equal to -1. The only special case is this rule to add power 1 and divide by new power if n does not equal to -1. If it equals -1, you need to have ln. So differentiation of ln is 1 over x. Okay, so here, this just ln t. t2 minus t1, ln t2 minus ln t1, or ln t2 over t1, ln t2 over t1, that's it. Plus, the same here, r is constant, this guy is constant. So dv over v, same way, ln v2 over v1. This is delta s, or you can write delta s like this. How about if you use the other equation, this equation, repeat it yourself, you will find S2 minus S1 equal Cp ln T2 over T1 minus V over T, so minus R ln P2 over B1. The similar equation. So if you use this equation and divide by T became delta S. Divide by T, delta T over T. Divide by T, V over T. V over T is R over P. Put here R over P. Integrate. This will be ln T over T minus R ln P over P, which is ln P2 over P1. Okay, guys? Does it make sense? These two equations valid only for
Gases.
ideal gases,
Ideal
not only
gases.
gases, ideal gases. We assume inviscid gases. It has no friction. It has no losses. Okay, guys? This is called ideal. Ideal means inviscid, non-viscous, zero viscosity. Like Euler flow, it's Euler equation. All of these are for ideal gases. Okay, guys? Okay, any questions so far? So we finish all of them. So how can you can get delta S for constant temperature system from steam table for liquid and solid? Liquid and solid is so easy. Actually, liquid and solid, this is volume is constant. It's just this special case. CV, this is liquid and solid. Now it's for ideal gas because we have V2 over V1 because ideal gases, it changes its specific volume. It changes volume with compression or expansion. Okay, guys?
So then the second equation is used if there's a change in pressure, basically.
Both are correct. Look.
Okay.
Look at this. Look at this. The first equation, exactly the second equation. Exactly. You know how? Do you remember when I said Cp equals Cv plus R? Do you remember this, guys?
Yeah.
If you replace here Cv plus R, so Cv times this give this. R times this minus R times this. If you take R common factor, you will obtain P2 T1 over P1 T2. This one is actually V2 or actually V1 over V2 over V1. Actually V1 over V2. Then to make it positive, reverse it, you're gonna obtain this equation. So if you replace, for example, Cp equals Cv or plus R, put it here. The first time this, the second time this. The first time this is equal to this. Okay. The second time this minus this, if you combine together, it will be exactly this term. Exactly. So this equation identical for ideal gases. And also we said Cp over Cv equal what? Can somebody tell me what is this? Cp over Cv? Chapter
K.
3. K. Exactly. A specific heat ratio or gamma. Some people use gamma, some people use K. Both are correct. K or gamma. A specific heat ratio. For example, for air, Cp 1004 joule per kilogram Kelvin. Cv 717. R 287. This plus this equal exactly 1004. This over this exactly 1.4, which is K. Cp over Cv for air, open table 1, you will see Cp, or actually table 2A, A2A, you'll find Cp over Cv, which is K, given a specific heat ratio. A specific heat ratio. Cp over Cv. K, some books use gamma. Both are correct. It means the specific heat at constant pressure or divided by specific heat at constant volume. Okay, guys? You got all of them? Okay, guys? Okay, guys?
Yeah.
So now you can obtain so easily delta S for ideal gases. Okay. 7.9. Before that, we can derive something so important. It's called isentropic for ideal gas. Isentropic flow. You don't need this to know this revision, but if you know it, it's good. Sometimes I give it as an extra problem in the exam. Derive for me this. Isentropic, guys, mean delta S equal to 0. Delta S equal to 0. So if you pick up the first equation, the second equation, and you combine them together, and you put delta S equal to 0. So for example, equation 2, 0 Cp ln T2 over T1 minus R ln P2 over P1. You can take this power, you can take this power, you get this other side. So T2 over T1 to the power Cp equal P2 over P1 to the power R. R, guys, it's actually Cp minus Cv. So you can say T2 to the T1 to the power Cp divided by Cp minus Cv equal P2 over P1, which is P proportional to T to the K over K minus 1. That's it. Divide by Cp, Cp over Cp, Cv, sorry, Cp over Cv is K. Cp over Cv is K, minus Cv over Cv is 1. So this is called isentropic correlation. In the exam, you can use this only. So P inverse proportional with V to the K. Actually, you have seen this before, guys. I will show you how. Where did you see it before? Or the last one, which is P with V with T. V with T. Which combine both together. Okay, guys, you don't need to know this derivation if you want. That's okay. In the book, you can just use P V to the K equal constant, which is the last one I obtained. This one. This, guys, you saw it, you have seen it before. I use the power N. I call it polytropic. And we have, for example, a lot of special cases. If N equals 0, this is called isobaric. If N equal 1, it's called isothermal. If N equal K, we call it isentropic. If just N, it's called polytropic. If N goes to infinity, we call it isochoric. Anyway, all of these cases, guys, this 4 or actually 4, but this is generally like this. Where we used them before. If you remember when we set W equal PdV, and we wish to have P function of V, there is a very important correlation called PV to the N equal constant. Pressure, V to the N. Ideal gas, PV equal RT. This is always correct for ideal gas, always correct. Sometimes, and some doctor prove that P times V to a certain power equal also constant along with this. So this equation, this is always correct. Sometimes this is also correct with a power, for example, N. N, generally, if it's N equal K, K is specific heat ratio, we call it isentropic. P V to the K equal constant. It means, if you come here, guys, if you come here in this formulation, and you put some temperatures and some volume, which one? I don't have it here, but it's okay. Let's talk about this one. P T to the K over K minus 1, which is this equation. If you put this T over T and P over V with certain ratio, this equation will be 0. 0 means isentropic. What is this? And this ratio is, it's like this. P1 over P2 equal T1 over T2 to the power K over K minus 1. Always will be 0. We call it isentropic. If you have P1 and P2 and you have T1, you can obtain T2 from here. For example, you have K. Let's say I told you for an exam, this is air. This is air. You can get K from table A to A. Please open table to A. You will find for air K equal 1.4. And you have P1, what atmosphere? B2, 5 atmosphere. You have T2 or T1, 500 Celsius, converted to Kelvin. You can get T2. Let's say 1000 Kelvin or something. So from this correlation, you can get T2. If you plot this ratio here, and you put this ratio pressure here, of course, delta S will be 0. Because this equation is called isentropic. It means I can obtain pressure ratio, temperature ratio to make this 0. So actually, we start from here. We simplify this when it equal to 0, and it use it, reduce it until we obtain this equation. It means P over T equal T over T to the power something. This is called proportional. So if Y proportional to X, it means Y2 over Y1 equal X2 over X1. This is called the same slope. The ratio remains the same. So you can say either Y equals C times X, or divide Y2 equals C times X2, Y1 equals C X1. Divide, so C will be gone. So this called constant of proportionality can be removed if you use ratios, like here. So pressure, direct proportional with temperature to the power K over K minus 1. K is specific heat ratio. And we drive it. Delta S equal to 0. I put the left hand side equal to 0. Equals Cp ln T2 over T1 minus R ln T P2 over P1. For logarithmic functions, ln, we can use the coefficient as exponent. Coefficient exponent, and take this other side. So R times P ln P2 over P1 equals Cp ln. Cp can be power, R can be power. Ln will cancel ln. Ln cancel ln. So T2 over T1 to the power Cp equal P2 over P1 power R. R equals to Cp minus Cv. So I can say it's Cp minus Cv. Take root of Cp minus Cv. Root of Cp minus Cv. It means divide in the power. If you divide the both sides by the same power, you get root. So if you have, for example, x squared, you got the square root, it became x. Because you divide this 2 by 2. If you have power a, you get root b, it means x a to the p. So Cp divided by Cp minus Cv. Here Cp minus CV over CP minus CV, which is 1. CP, divide here CV, divide here CV, divide here CV. CP over CV is K. CP over CV is K. CV over CV is 1. So it's K over K minus 1. Is P proportional to T power K over K minus 1. Hey guys, I'm fast?
No, you're good.
No, for others. Guys, I'm fast. Anyone see I'm fast? It's okay, you can say. First of all, I'm using math. It's, you know, of course, you know this power exponents length. I assume you know that you are almost like, I don't know, 2-3 years engineering. So even high school, ln powers, this kind of ratios, it's like everyone know it. This direct proportional, it can be ratio, this powers, treatment of integration or differentiation on manipulation of a logarithmic function. I think all of you know that very well. So I believe you following me. Okay, guys?
Yeah.
So finally, we need to go this way. PV to the K, which is PV to the K equal constant. It means P pressure inverse proportional with V to the power K, which is this equation. This only valid if it's isentropic. Here is polytropic. If N equal K, we call it isentropic. Only if it is ideal gas and isentropic. So PV to the K equal constant. Or P2 V2 to the N equal P1 V1 to the N. This means constant. Or P inverse proportional to V to the K. This is the same meaning as this one. P inverse proportional to V to the K. Okay, guys? Does it make sense for you? Hey, guys? Hello?
Makes sense.
So for now, for steam table, it's easy. S1 equal S2. If you have isentropic, S1 equal S2 from a steam table. Steam table is very simple. Move vertically. Let's put it here. So this equation valid always, correct always. Solid, gas, anything. This equation only for gases. This part only here for what, the guys? This one is what? Only for what? This part.
Solids and liquids.
Pure solid and pure liquid. Perfect. If you have pure liquid, does not change to vapor. This is Trump style. If you have this, do that. So this is always correct. If you have liquid, pure liquid, and pure solid, use a lot of gesture in his talk. You know Donald Trump, guys, correct? Anyway, so delta S equal this. So we have also the TS diagram, something like this. If I said to you, you have isentropic, it's just you move vertically. Let's say 1 to 2 or 2 to 1 or 1 to 2 vertically. So you are moving vertically. S1 equal S2. It means isentropic in this process from 1 to 2. Okay, guys? Hello?
Can you repeat that?
Okay, in TS diagram, or actually in a steam table, you can obtain S. If you have two independent intensive properties, you can go to the table, like today's quiz. You can obtain S1, you can obtain S2. Correct? Correct?
Yep.
Great, that's what I want to hear. Yes, we can obtain from a steam table, you can obtain S1 and S2. If I said in a problem using steam table, the second category, if we have this process isentropic, you can obtain S1, for example, from point 1, give it to point 2, state 2. It means you move vertically in TS diagram. If I told you you have rigid tank, let's say this is PV diagram, it means you move vertically, let's say from here to here, from here to here. This is called isochoric, constant volume, correct? 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 Vertical in PV diagram, it means constant volume. Volume here, same as here. Correct?
Yeah.
This is called as what? In TS diagram, entropy. Entropy here is same as here. So sometimes, if I said isentropic, no losses, Carnot cycle, you can use S1 from state 1, give it to state 2. It means I will not give more information in state 2. I will give you only one. Let's say, for example, quality. So from quality and S1, which is S2, you can obtain everything here. The pressure, temperature, and volume, and internal energy, enthalpy, everything can be obtained at 2 if you only have another, because S1 equals S2. From this one, you can easily obtain this from, let's say, T and V, P and T. Any two independent property, you can get one. One of these properties is called S1. Give it to S2 if it is isentropic. If you have here, let's say P and T, you can obtain, for example, V1. Give it to V2. So you need only one information at 2 because it's a rigid tank, for example. So isentropic means two things: adiabatic and reversible. Very, very ideal. We try to approach it. Yeah, for some process we obtain like up to 95% kind of reversible process. We are very almost reversible, 95%, but we wish to be 100%. So we have no losses, as we will see in the next part. So let's take 7-minute break until 11. Let's continue. The coming part is much better than that. We still stick to the entropy, but we're gonna go from another perspective. First of all, you need to make sure that you understand what is going on here. I will give you one simple example, for example, here. Let's say I told you we have an ideal gas. We have an ideal gas. Ideal gas. And I give you just T1 and let's say V1 and let's say T2, for example. Only T1. Let's say T1 was 300 Kelvin. There must be Kelvin. V1, like let's say 1.3. Actually, that's a big number. Let's pick a 0.001 meter cube per kilogram. And T2 was like, let's say 400 Kelvin. And I said this process was isentropic. You have three formulas. You have three formulas in this part. We're gonna take the VT correlations. Go to page, lecture 13, page 12. You will see that T inverse proportional to the VK minus 1. Because it's isentropic, I'm sure that S equal to 0. So if I want from here, for example, let's say I want P2. I want anything else. From this, you can obtain here P1. Let's say I want delta U, delta H, whatever I want. Sometimes we need this. Because if it's compressor turbine, we need delta H. Let's say I want delta H. You can easily obtain P1. You can easily obtain U1. You can obtain H1. But when you go to 2, you don't have anything else. You need two independent intensive properties. But you can use S1 equal to S2. You can put it here. So you can use either this, T2 over T1. So you have this, you have this, you have this. So you plug it in here, you can get V2. So you have T1, you have T2, you have V1, you don't have V2. You can obtain V2 from this by putting it equal to 0. Or just use this equation. T proportional to V to the K minus 1, which means T1 over T2 equals TV opposite. It's V2 over V1 to the power K minus 1. You have T1, you have T2, you have V1, you can get V2. Only you can get V2 here. K is from table A to A. Let's say this is air. You can easily get the K. So you can get V2. Just simple equation. The same as this one. This is for only ideal. Do not use it for anything. Only ideal gases. So this would be part of the problem. Part of a problem. In a quiz, I can give you ask you for this only. But when you have a problem, let's say you want to, for example, I want to get maybe Q minus W, or actually no, if you have like turbine, you have energy coming in, energy going out. This is turbine. This is 1, this is 2. So you want to work done, it's delta H. Work per unit mass is delta H. So we want to get delta H. Let's say you have here. Let's say you have T1, V1, V2, but I said isentropic. So you have V1 over V2, and this is equal to 0, we can get T2. So this guy, just Cp delta T. So I wish to have T2. The only way, through isentropic. To obtain delta H, we need to say delta T. Because it's ideal gas. Let's say air. Cp is given, T1 is given, T2 I don't know. So from where I can get T2? From this correlation. Let's say I give you P1, P2. You can use the other equation, which is P proportional to T, K over K minus 1. So it means P2 over P1 equal T2 over T1 to the power K over K minus 1. 1.4 over, usually, because I'm smart, no. Because I want to save time, I used to use this 3.5. 1.5 over 0.5, over 1.4, sorry, 1.4 over 0.4, it's 3.5. So because I know this value in advance, I used to use it for air, it's 3.5. So I have P1, put it here, T2, I can actually obtain, I can obtain T2. Take this to the power 1 over 3.5, so this would be gone. Multiplied by T1, you can get T2. T2 equal T1, this to the power 1 over 3.5. 3.5 because Ka is 1.4. Divided by 0.4 is 3.5. Okay, guys? So sometimes, not because we are small, no, because we see the same thing over and over and over. That's why this 3.5, I remember it from even before your age. It's by the first year of mechanical engineering, aerospace engineering. So I was aerospace engineering originally. So this ratio is just 1 over 3.5 for the pressure side. Okay, guys, any questions? Any questions? So again, very simply, again, when I said isothermal, iso something, it means something is constant. So I don't need to give you the two temperatures. If I said isothermal, take T1, give it to T2. Isobaric, take P1, give it to P2. Isochoric, isometric, take V1 to give it to V2. Isentropic, take S1 to S2, or use this formulation for ideal gas. So isentropic, it's reduction in the given in one state, equivalent to a reduction. I don't need to give you two independent intensive properties. I only need to give you one if it's isentropic correlation, because you can use this pressure ratio, temperature ratio, volume ratio to obtain the missing piece. Okay, guys? Does it make sense now? Does it make sense now, guys? Does it make sense, guys? Does not?
Yeah, makes sense.
So the only thing you need to exercise a lot. The more you exercise, the better you are. And also, we're going to solve a lot today in everything, steam table. So let's move to the last part before we solve. Do you want to solve now, or hi guys? Do you want to solve some problem now? Yeah. Okay, let's solve some problems before we move to the next part, which is the last part of the lecture. Reversible work. Let's take some more exercise. That's good for your practice. 741. Please, everyone, read problem 741 in your book. 741. We're gonna solve this problem by numbers. So read it carefully. 741. I already removed chapter 7 to 12 from the. I wish that all of you download them. Download them as I said before. If you did not, take it from somebody else. Okay, 741, it says you have a tank. It's a rigid tank. It has 5 kilograms of water. The initial state, T1 was 100 Celsius. Quality was 100%. Completely vapor, saturated vapor. At state 2, temperature was 25. So I cooled down the tank. I cooled down the tank. I get heat, cool down. The first required, A, sketch on TV diagram. That's very easy. Determine delta S system in kilojoule per Kelvin. So delta S capital, not small. Small is specific. Determine the generated or the total delta S. It means delta S system plus delta S surrounding. Of course, must be greater than or equal 0. Because we have heat, it's impossible to be 0. It must be greater than 0. 0 means isentropic. Isentropic means adiabatic, no heat, and reversible. So this has two things, need to be adiabatic and reversible. If you don't have adiabatic or reversible, this is impossible to be. So this process is reversible, yes, but is not adiabatic because you have heat. Of course, you have delta S. So delta S must be greater than 0. But it can be 0 if you have both adiabatic and reversible. Like, for example, turbine, compressor, pump, there is no heat. But boiler, no, boiler has heat. Evaporator, condenser. If you have heat transfer, delta S must be greater than 0. So this process, rigid tank, I took heat, cool it down. What is the most important thing here, guys? This is rigid tank. What do you learn from this? Rigid tank, guys, what does it mean? Hello, hello. Rigid tank means what? Can you hear me, guys?
Yeah.
Rigid tank means what?
Constant volume and constant mass.
Exactly, constant specific volume. That's one word, perfect. Mass and volume are constant. Of course, no mass in, no mass out. No volume will change. It's a rigid tank. It's exactly like this. My wife bottled this, but I open it. This one. It's like exactly. It's, you know my wife, she used to put here, like, I don't know, like state 1, it even superheated vapor. So here, guys, we have V1 equal V2. State 1, you have two independent intensive properties. The very end of saturated mixture, saturated vapor. Get V1, give it to V2. So you have two things at state 2. So you can continue the solution, anything you want. The first required, so easy. Actually, what we said, we move vertically in the V direction, constant V. So the first part is so simple. You can plot it here or there. Let's plot it here, there. TV diagram, something like this. TV diagram. State 1, exactly saturated mixture. This is temperature 100. This is temperature 25. T equal 100. T equal 25. Exactly like you plot X, Y. I told you Y equal 3. Y equal 1. Y equal 9. Y equal, it's a vertical, horizontal line perpendicular to Y. Y equal constant. If I said X equal 0, this guy, X equal 0. X equal 4. It means this point is 4 and 3. X equal 4, Y equal 3, and so on. Exactly Cartesian or Cartesian coordinate systems. So this point, guys, X equal 0 to X equal 1. This one, X equal 1 and T equal 100. So this is state 1. How can I move vertically? Either this way or this way. He said to 25. 25 and constant volume, it means this is the point. That's it. You got 4 out of list 12 just by this sketch. Let's say this problem was like 20 points. You can get 5 points here just simply by doing that. You know, this curve, there is no x. This is x equals 0. There is no x here. 0, 0.1, 0.2, 0.3 up till 1. There is no x here. So you know 100 Celsius. Guys, if I told my son, if he's what, 4th grade, 5th grade, he knew this is line constant y. This is constant y. This is constant y. What constant temperature? This is the first point because x equal 1 and t equal 100. Rigid tank, it means move vertically, anywhere vertically. I cool it down. Of course, temperature decreases until 25. It's here. Does it make sense, guys?
Yeah.
Okay, before you do anything, let's write down what you want. This is done. This one, I used to write notes on the side to see what I want. I want delta S system, delta S total. This will be, so delta S system equal. This is heat addition to a system, correct? Which means this is steam table. So it means if you want specific or you want total, so it's mass times S2 minus S1. Why? Because this is called steam table. I want to have S2 from state 2 and S1 from state 1. This system does not have constant temperature, for example. The surrounding, yes, but this system, no. So I want system, M is 2. So this one was number 2. We have number 1, constant temperature, steam table, solid and liquid, ideal gas. You remember these 4 cases, guys? This is number 2. And of course, you remember the definition always, Q over T. That's always remember. If I have Q function of temperature, I can integrate to obtain S function of T. So always remember the basic definition and the special cases. This is the second case, which is steam table. So I wish to have S2 and S1. How about the last one? The last one is simple. Delta S total or generation is delta S system, which is I will obtain here, plus delta S surrounding. So delta S surrounding is just Q over T. And Q, this is closed system, is just delta U. So I want to have M delta U. U2 minus U1, M, U2 or minus U1. So I want to get at the state 1, S1 and U1. At the state 2, S2 and U2. But I cannot get S2 or U2 because state 1 incomplete. So I need also V2. That's why I will get a V1. That's what I get. At 1, I need V1, S1, U1. add 2. I will start with V2 and T2 to obtain S2 and U2. S2 and S1 for the second required. U1 and U2 for the last required, because I need Q. How much heat added to the ambient. Removed from my system, added to the ambient. Okay, guys, does it make sense for you?
Yeah.
Some people, which is I don't like, for state 1, he said, I have 6 variables, I get everything. I will give you P1, H1, U1, V1, S1, everything, which is waste of time. You need to know what properties you need. So write kind of dummy equation, what you want. I want this, so it need this, it need that. So I need you this and this. I don't need H's. I needed pressure, unless it's needed. So you need to know what you want before you solve, to save time when you use the table. Okay, guys? Because sometimes you have interpolation. Sometimes you need to do quality calculation. That's not easy. So at state 1, guys, at state 1, where I have T1, that's very easy. T1 is 100 Celsius and X1 equal 1. It means use everything with letter G, the vapor. So V1, at this temperature, use VG, SG. This is specifics, UG. And they are, if you open table A4, you will obtain these values are 1.67. Actually, I wrote this number many times. Meter cube per kilogram. Don't forget the units, please. 7.3542 kilojoule per kilogram Kelvin. 2506 kilojoule per kilogram Kelvin. Actually, no Kelvin here. I'm sorry. This is specific energy, but this is a specific entropy, which is, yeah. Now take V2 to V1, which is 1.672, correct? Meter cube per kilogram. And T2 equal to 25. Look like this is saturated mixture. So which table, guys? Which table? Mixture. Mixture air, mixture water.
Table A4.
Why? Why? Why not A5?
Enough temperature.
Because the temperature is input. Perfect. Temperature is input. The tables, fortunately, wasn't Celsius. But when you have equation, like for example, ideal gas law, or even equation, you are substituting temperature, you need to have it in Kelvin. So A4, this is mixture. It means at this temperature, you will find your V is in between VF and VG at this temperature. Correct? So you need to get X2, which is V minus V2 minus VF2 over VFG, which is VG2 minus VF2. It's a very huge VG2. You'll obtain X equal 0.03856. So you were 100% vapor, you became almost 4% vapor, less than 4% even. In mass, in terms of mass. Can you see that, guys?
Yep.
Can you see, can somebody tell me VG equal to what? VG for X2 equal to what? For state 2? VG equal to what? Table A4 at temperature 25, what is VG? Can somebody tell me, guys? No one?
So 43.30.
Can you see the number? 43 meter cube per kilogram. It's almost an area of like a small room. Correct? 4 by 3 by 4 almost. Area of a room, guys. It's a huge area for 1 kilogram because the pressure is so low. So this VG is so big. This one is 1.67. 2 meter cube. Almost meter by 2 meter by meter. Almost 2 meter cube for every kilogram. This one and this one almost the same. 0.001 something. 100 like something. Almost 0.0 or 11. There is no much change in the VG, in the VF, sorry, in the left VF at x equals 0. But there is a significant change in the VG. Can you see that, guys? So this curve is like, we went to 43 meter cube. That's a huge number. However, you can feel it because the temperature is so low and the pressure is so low, you can easily expand this. Because the pressure is so low, it can go almost more than 20 times incubation the same. So this is like 2 became 43, more than 40 times or 20 times. Like this volume became 20 times because of reduction in pressure from almost 1 atmosphere to maybe like 20 or 30 kilopascal. Okay, guys, does it make sense for you? So you need to feel the number when you get it. You need to understand it more. You can easily get SC2 now and U2. That's what we want. It's SF plus X SFG. And unfortunately, we have FG, SFG. We don't have this, but we have SFG, the middle column in S, the middle column in U. It's called UFG. Because we can use these numbers a lot, we insert an additional column for U. It's called SFG, UFG, which is SG minus SF. Actually, we don't need, you can calculate them, but because this saves some time for you to use abstraction directly. Okay, guys? Make sense? So S2 was 0.6. Oh, that's decreased. That's expected. Kilojoule per kilogram Kelvin. While UG also UO decreased because the energy of the system decreased. So it was 2,500 became almost 200. 2,000, almost 1/10 of energy. So when you have water, energy 200, 300, there's almost water, almost pure, almost, there is no vapor, almost. But this guy, 200, this is 2,500. So energy decreases a lot because you cool down the system. Water in the liquid phase, it has a much lower energy than vapor. This is complete saturated vapor, X equal 1. Okay, guys, make sense? Okay, guys? Okay, guys?
Yeah.
So mass 5 kilograms. Of course, in closed system, you will not see dot, you will see mass. But open system, you see m dot because it's the rate. Then delta S, which is minus 33.327 kilojoule per kilogram Kelvin. Why it's negative? You know why it's negative, guys? Can anybody tell me why it's negative?
Because heat is leaving. System.
Exactly. Heat is negative. Perfect. According with respect to the system, heat is negative. But because temperature is not constant, I cannot say Q over T. If the temperature is constant, yes, I can say Q over T. But temperature changes. That's why we need to use steam tables to get S1 and S2 and get abstraction. Okay, guys? Make sense now? But of course, because heat is rejection, I don't know how much heat changes with time. Of course, this integration is negative. Of course, because heat is rejection. But this is the same heat, guys. with respect to the surrounding is positive or negative?
It's positive.
For respect to surrounding, yes. So we need to get Q. So Q equal M delta U. So you have U2 minus U1. It's negative with respect to the system, yes. Whatever value. Make it positive for the surrounding. This is Q kilojoule, because you have here, there is no kilogram here. Just kilojoule per Kelvin, because we multiply by mass. So get this Q, it's negative for the system, yes. The Q was 30, I did not get the Q as it is. Anyway, you get this Q. If you have U2, U1, you have mass 5 kilogram, you can get this Q. With respect to surrounding is negative. So delta S surrounding, which is just simply Q over T, and T was the same as 25. So 25 plus 273. Do not ever, never, ever use Celsius in this ratio. In any temperature, use Kelvin in any equation, like this equation. It was 38.778. That's great, guys. That's great. You know why? You know why that's great? Because it's bigger than minus 33. That's awesome. Okay, guys? So the total would be positive like 5 or something, 5 point something. Okay? If you get delta S generation, minus 33.28 plus 38, it's bigger than 0. Perfect. That's awesome. Okay, guys? Any question, guys? Let's back for the last 10 minutes or 15 minutes. We need to go back to the lecture. Again, I'm gonna send you more problems in this. No problems. We can add more additional problems for you in videos. But let's stick now to the lecture. So we can easily use steam table, constant volume, constant temperature, even gases, as you will see. So now let's go back to work. Again, 7.10. There is something called reversible steady work flow. Steady flow work. Look at this, guys. For compressor, pump, for turbine, many components, as long as there is no heat, because there is no heat in those, adiabatic, and also they are reversible, we can assume they are isentropic. For now, let's say they are reversible only. There is no heat loss. If you don't have heat loss, or at least reversible, you can say those. Look at this. Generally, always correct. W is integration of PDV. That's always correct. Reversible or not irreversible. Area under the curve PV is the work. This is work per unit mass. If you multiply by mass, it will be multiplied by mass flow rate, it will be power. W dot. Okay, guys? Okay, guys?
Yeah.
Okay, delta Q, first law of thermodynamics for this open system is delta Q minus delta W plus a steady, let's say steady, so it's equal delta H plus delta kinetic energy plus delta potential energy. For now, I relate those, or they are constant. It's okay. We have this guy is T delta S, which is delta H minus VDP. So if you go back to the previous lecture, part of the lecture, we said delta Q is T delta S. Delta Q is T delta S, ds, which is dH minus VdP. Go back, we have two formula, either du plus VDP, correct? Or DH minus VDP. Remember this, guys? Actually, PDV. Something like that, correct? Correct, guys? Go to Brazil lecture. Look at this part. Okay, guys? Hello, hello?
Yeah.
But this is only happen if this is reversible and this process is reversible. So this delta H will cancel this delta H. If you replace this by that, this cancel this. So delta W now equal minus VDP minus delta kinetic energy, delta potential energy. If you keep them, it's okay. Or W reversible, only reversible. It's integration of VDP minus delta kinetic energy, small of course, minus delta potential energy small. So this is called reversible work. Only if you have reversible process. Minus VDP. So this is PDV, always correct. This is minus VDP. If you neglect those, usually we neglect those, but keep them now. This is, guys, is VDP. Okay, guys? So this equation, reversible work. Open system. Must be open system. Steady flow. These are three assumptions in this equation. Must be reversible work, reversible process, like pump, compressor, turbine, and any other device. It has work. It has work. Let's go to special case. If, let's say, if volume is constant, guys, this is open system. I cannot say, for example, tank, rigid tank, or piston cylinder. This is open system. If the volume is constant, like what, guys? Do you know what? Like what? Like pump. Pump is a very famous problem. Pump is a device that compress water, almost coming 0.001, going out 0.001. Density does not change, almost. The pressure was 1 atmosphere, can be like 5 or 10 atmospheres. There is almost nothing change. Here 0.01, here can 0.001, like maybe 105, like less than 5%, 2%. Almost V1 equal V2 in pump. So you can assume V equal constant like this. So if V equal constant, this can be out. So just W reversible can be minus V, which is constant, delta P, P2 minus P1 plus or minus delta kinetic energy minus delta potential energy. This is the work reversible if you have constant. Very famous, the pump. Pump is a very famous. You will see it a lot when you go to Rankine cycle in chapter 10 and 11. Chapter 10 and 11 for the regeneration. So V equal constant, like liquid. If you have liquid, if I give you this liquid and you want to pump it to the 10th floor, give some pressure and then come pump up to have potential energy. So change the pressure to potential energy, like the pump in the house, in the building, very tall building. So what happened? The volume does not change that much, almost constant. Almost constant. Okay, guys, does this make sense for you? Okay, guys?
Yeah, it makes sense.
So let's say another case if there is no work. Process reversible but no work, like for example nozzle, diffuser. So this equation, if there is no work, so you can say with volume is constant also, VdP, or maybe P2 minus P1, actually negative can cancel each other. So multiply everything by negative. So it will be just yeah, that's correct. It's plus delta kinetic energy plus delta potential energy equal 0. Do you know what this, guys? Do you know what this equation, guys? You have seen it many times, even in high school. If there is no work, this equation. Let's write it. You know what this? This is 1 over rho. This is like half v square, velocity square. Forget about this now. If you have 1 over rho delta p plus half rho v square velocity equal constant, or 0 delta, or delta p plus half rho delta v square. You know what this is, guys? P1 plus half rho v1 square equal P2 plus half rho v square. What is this, guys? You know what is this equation? It's a very famous equation. What this equation, guys?
Bernoulli.
Bernoulli's equation, perfect. Bernoulli's equation. The total energy is constant. This is a free fall of a pin. This plus this equal constant. The flow over airfoil, the pressure increases, velocity increases. In kinetic energy increases, pressure decreases, and so on. They are inverse proportional to each other. Pressure increase, velocity decrease. Velocity decrease, pressure increase. Pressure decrease, velocity increases, or kinetic energy. This is Bernoulli equations. How many have seen it many times? The total energy is constant. Just if this is Bernoulli also, we replace this, and simplify it, became a very famous form of Bernoulli. So it's no friction, incompressible. So the last part was isentropic efficiencies. Okay, guys? So I'm not gonna go to equations, but I'm gonna tell you facts. And we're gonna use these facts in the coming lecture. The coming lecture, next lecture, Wednesday, I'm gonna discuss this. But today, just I'm gonna give you the hints. So I'll give you a video with some more problems for you, for ideal gas, the midterm 2, of course, sample. I'm gonna post it to you Friday, so you can watch it. So what happened, guys? We have compressor, we have pump, we have turbine. Turbine can be gas turbine or steam table. Let's start with compressor. Compressor, let's talk about gases. Let's talk about the TV diagram. The gas is constant pressure line like this. The pressure line are diverging. This is the key of all designs. The pressure lines P1 and P2 are diverging. When we go to about Rankine cycle, Otto cycle, Diesel cycle, Brighton cycle, Hamida cycle, inshallah. So these cycles are always, pressure lines are diverging, going away from each other. This is the key part of all devices. The same for turbine, for example. Turbine also, everything diverging like this. The pressure line are going away from each other. Always. Even if you plot this diagram, the pressure line here, the other one is here. It's always diverging. So this is air. We are plotting this part, which is the superheated part of air, which is this one. The same for turbine. The same for pump here. This parallel line usually for pump. So what happened here, guys? This, let's say now for air. Air is simple. Air, let's say we have Cp constant. So you can T or H, they are the same. H just CPT, just a stretch, but the same thing. So you are here, let's say you are here, and I want to compress it to here. If this is Ts, I wish to move vertically exactly like this. 0 delta S. I wish to go isentropically between 1 and 2. I wish. That's a wish. This is, we call it 2S. So in compressor, I pay work. This work, exactly this distance. H2S minus H1. This is exactly what I wish to pay. Unfortunately, we have some friction, we have some heat, we have irreversibility. So entropy generated. So we move reality in the blue or red line, like this. This is actual. So we pay more. Oh, that's W actual. Oh, that's cool. So we wish to go vertically from 1 to 2 S. Remember, 1 to 2 S, we can use the isentropic relation. For example, this T and V can be proportional, like P proportional to T or K over K minus 1. Only along this line. Let's look at the black line. Isentropic. The isentropic line, this one, P proportional to T, K over K minus 1. Only along the black line, because it's isentropic. Delta S equal to 0. From 1 to 2S. This process. But in reality, we have this losses. We pay more. We pay more work to go to the same pressure line. We pay more work to go to the same. Well, I wish to go from 1 atmosphere to 10 atmospheres. If I go vertically, I pay this amount of energy, H2S minus H1. But unfortunately, because of friction losses in the system, I go a little bit slanted with a slope, with more delta S. Unfortunately, is not equal to 0. This is actual. Sometimes we use A. So I pay H2A minus H1. H2A greater than H2S minus H1, of course. I pay more work. This ratio, the small over the big, we call it isentropic efficiency. We're going to discuss it next lecture. How about turbine? The same thing, but turbine, I'm here. This is one, the entrance to the turbine. I want to expand, go from 5 atmosphere to 1 atmosphere. I wish to go from 5 atmosphere just to 1 atmosphere. This is the 1 atmosphere. Pressure line diverging. If I have a very good design, perfect design, I go vertically downward with 0 delta S. This is TS diagram. I wish to go to this point directly, 2S. So I get too much work. This is what I got. H1 minus H2S. It goes from high energy to low energy. Pressure from high atmosphere, let's say 1 atmosphere. Expand through the turbine. But what happened in reality? The red line, I have delta S, some losses. Which one is taller, guys? The red line is taller or the black line? Which one is taller?
Black line.
Of course, what you get isentropically more than actually 2A. Opposite to this. But here I got this less than what I'm supposed to get because of losses. Here I pay more what I'm supposed to pay because of losses. Does it make sense for you? Does it make sense for you guys?
Does the black line represent ideal conditions, or is this just like a point of reference?
No, it's exactly both. That's what I wish. That's a good reference. That's a perfect example. That if I have delta S equal to 0, which I can use these equations, for example, delta S equal to 0. Remember the equation of delta S? CV len, or actually CV len T2 over T1 minus, I wish to be 0. I wish. Correct? Correct, guys? I wish to be what?
0?
Yes, I wish to be 0. Okay, now please go ahead and in files, and there is a quiz now.